Section 6.3, Line Spectra and the Bohr Model. The work of Planck and Einstein paved the way for understanding how electrons are arranged in atoms. In 1913, Danish physicist Niels Bohr offered a theoretical explanation of line spectra, another phenomena that had puzzled scientists during the 19th century. We'll examine the phenomena and then consider how Bohr used the ideas of Planck and Einstein. Section 1. Line spectra. A particular source of radiant energy may emit a single wavelength, as in the light from a laser. Radiation composed of a single wavelength is said to be monochromatic. However, the most common radiation sources, including light bulbs and stars, produce radiation containing many different wavelengths. A spectrum is produced when the radiation from such sources is separated into different wavelength components. In Figure 6.11 shows how a prism spreads light from a light source into its component wavelengths. The resulting spectrum consists in a continuous range of colors. Violet merges into blue, blue into green, and so forth, with no blank spots. The rainbow of colors containing light of all wavelengths is called a continuous spectrum. The most familiar example of a continuous spectrum is the rainbow produced when raindrops or mist acts as a prism for sunlight. Not all radiation sources produce a continuous spectrum. When a high voltage is applied into tubes that contain different gases under reduced pressure, the gases emit different colors of light. The light emitted by neon gas is very familiar, red-orange, of many neon lights, whereas sodium vapor emits a yellow light characteristic of some modern streetlights. When light coming from such tubes is passed through a prism, only a few wavelengths are present in the resultant spectra, as shown in Figure 6.13. Each wavelength is separated by a colored line in one of these spectra. A spectrum containing radiation of only one specific wavelength is called a line spectrum. When scientists first detected the line spectrum of hydrogen in the mid-1800s, they were fascinated by its simplicity. At that time, only the 4 lines in the visible portion of the spectrum were observed, as shown in Figure 6.13. These lines correspond to the wavelengths of 410 nanometers, which are violet, 434 nanometers, blue, 486 nanometers, blue-green, and 656 nanometers, red. In 1885, the Swiss schoolteacher named Johann Balmer showed that the wavelengths of these 4 visible lines of hydrogen fit an intriguingly simple formula that related the wavelengths of the visible line spectrum to integers. Later, additional lines were found to occur in the ultraviolet and infrared regions of the hydrogen spectrum. Soon, Balmer's equation was extended to a more general one called the Rydberg equation, which allowed the calculation of the wavelengths of all the spectral lines of hydrogen. Equation 6.4 is the Rydberg equation. In this formula, lambda is the wavelength of a spectral line, R sub h is the Rydberg constant, which is a number, and n1 and n2 are positive integers, with n2 being larger than n1. How could remarkable simplicity of this equation be explained? It took nearly 30 years to answer this question. Figure 6.12, Atomic Emission. Different gases emit lights of different characteristic colors upon excitation by electrical discharge. Figure 6.13, Line Spectra. Spectra obtained from the electrical discharge from A, sodium, and B, hydrogen. Light of only a few specific wavelengths is produced, as is shown by the colored lines in the spectra. Section 2. Bohr's Model. Rutherford's discovery of the nuclear nature of the atom suggested that the atom could be thought of as a microscopic solar system in which electrons orbit the nucleus. To explain the light spectrum of hydrogen, Bohr assumed that electrons move in circular orbits around the nucleus. According to classical physics, however, an electrically charged particle such as an electron that moves in a circular path should continuously lose energy by emitting electromagnetic radiation. As the electron loses energy, it should spiral into the positively charged nucleus. This spiraling obviously does not happen since hydrogen atoms are stable. So how can we explain this apparent violation of the laws of physics? Bohr approached this problem in the same way that Planck had observed the problem of the nature of radiation emitted by hot objects. Bohr assumed that the prevailing laws of physics were inadequate to describe all aspects of atoms. Furthermore, Bohr adopted Planck's idea that energies are quantized. Bohr based his model on three postulates. 1. Only orbits of certain radii corresponding to certain definite energies are permitted for the electron and the hydrogen atom. 2. An electron in a permitted orbit has a specific energy and is in an allowed energy state. An electron in an allowed energy state will not radiate energy and therefore will not spiral into the nucleus. 3. Energy is emitted or absorbed by the electron only as the electron changes from one allowed energy state to another. This energy is emitted or absorbed as a photon, E equals h nu. Section 3. The energy states of the hydrogen atom. Starting with his three postulates and using classical equations for motion and for interacting electrical charges, Bohr calculated the energies corresponding to each allowed orbit for the electron in the hydrogen atom. Ultimately, the energies that Bohr calculated fit a formula. Equation 6.5 is the Bohr equation embedded in the Rydberg equation, I think. In this equation, hc and rh are Planck's constant, the speed of light, and the Rydberg constant, respectively. The products of these three constants equals 2.8 times 10 to the negative 18 joules. The integer n, which can have a whole number value of 1, 2, or 3 to infinity, are called principal quantum numbers. Each orbit corresponds to a different value of n, and the radius of the orbit gets larger as n increases. Thus, the first allowed orbit, the one closest to the nucleus, has n equals 1. The next allowed orbit, the one second closest to the nucleus, has n equals 2, and so forth. The electron in the hydrogen atom can be in any allowed orbit. Equation 6.5 tells us that the energy that electron will have depending upon which orbit it's in. The energies of the electron of the hydrogen atom, given by equation 6.5, are negative for all values of n. The lower and more negative the energy is, the more stable the atom will be. The energy is lowest or most negative for n equals 1. As n gets larger, the energy becomes successively less negative and therefore increases. We can liken the situation to a ladder in which the rungs are numbered from the bottom rung up. The higher one climbs the ladder, the greater value of n, the higher the energy. The lowest energy state, n equals 1, analogous to the bottom rung, is called the ground state of the atom. When the electron is in a higher energy, less negative orbit, n equals 2 or higher, the atom is said to be in an excited state. Figure 6.14 shows the energy of electron in a hydrogen atom for several values of n. Figure 6.14. Energy levels in the hydrogen atom from the Bohr model. The arrows refer to transitions of the electron from one allowed energy state to another. The states shown are those of the n equals 1 through n equals 6, and the state for n equals infinity, which is the energy E equals 0. What happens to the orbit radius when the energy as n becomes infinitely large? The radius increases as n squares, so we need to reach a point in which the electron is completely separated from the nucleus. When n equals infinity, the energy is 0. Thus, the state in which the electron is removed from the nucleus is reference or zero energy state of the hydrogen atom. This zero energy state is higher in energy than the states which negative energies. In his third postulate, Bohr assumed that the electron could jump from one allowed energy state to another by either absorbing or emitting photons whose radiant energies corresponded exactly to the energy difference between the two states. Energy must be absorbed for an electron to move to a higher energy state, one with a higher value of N. Conversely, radiant energy is emitted when the electron jumps to a lower energy state with one lower energy value of N. Thus, if the electron jumps from an initial state that has equals initial to a final state of energy final, the change in energy is H nu. Bohr's model of the hydrogen atom states, therefore, that only the specific frequencies of light that satisfy equation 6.6 can be absorbed or emitted by the atom. Substituting the inner expression in equation 6.5 into equation 6.6 and recalling that nu is the speed of light over lambda, we have the change in energy. And this equation, n sub I and n sub f, are the principal quantum numbers and the initial and final states of the atom, respectively. If n sub f is smaller than n sub v, or n sub I, the electron moves closer to the nucleus, and delta E is a negative number indicating that the atom releases energy. For example, if the electron moves from n equals 3 to n equals 1, we have 1.94 times 10 to the negative 18 joules. Knowing the energy for the emitted photon, we can calculate either its frequency or its wavelength. For the wavelength, we have 1.3 times 10 to the negative 7 meters. We've not included the negative sign for the energy in this calculation because wavelength and frequency are always reported as positive quantity. The direction of the energy flow is indicated by saying that the photon of wavelength 1.3 to negative 7 has been emitted. If we solve equation 6.7 for 1 over lambda, we find this equation derived from Bohr's theory corresponds to the Rydberg equation, equation 6.4, which is obtained using experimental data. Thus, the existence of discrete spectral lines can be attributed to the quantized jumps of electrons between energy levels. Section 4. Limitations of the Bohr model. While the Bohr model explains the line spectrum of the hydrogen atom, it cannot explain the spectra of other atoms, except in a rather crude way. Bohr also avoided the problem of why the negatively charged electron would not just fall into the positively charged nucleus by simply assuming that it would not happen. Therefore, there is a problem with describing an electron merely as a small particle circling about the nucleus. As we'll see in section 6.4, the electron exhibits wave-like properties, a fact that many acceptable model of electronic structure must accommodate. As it turns out, the Bohr model was only an important step along the way towards the development of the more comprehensive model. What is the most significant about Bohr's model is that it introduces two important ideas that are also incorporated into our current model. One, electrons exist only in certain discrete energy levels, which are described by quantum numbers. And two, energy is involved in moving an electron from one level to another. We'll now start to develop the successor to the Bohr model, which requires that we take a closer look at the behavior of matter.